Hello everyone. In this chapter we're going to study numerical methods for approximating data points or functions. So there are basically two types of approximation. The first one is called a discrete approximation. You're given a bunch of points and you would like to find a function that will approximate these points. Now recall the idea of interpolation. The interpolation idea was to get a function that will go exactly through these points. Okay, so that's an interpolation approach. However, approximation, you're gonna find a function that is not necessarily exact. It will be a function that best approximates those 4 points. For example, you could approximate those 4 points with a straight line. So in that case, the straight line could be something like this. Okay, so that is the best quote unquote straight line that will approximate those 4 points. As you know, it's impossible to get a straight line that will go through all 4 points because they're not collinear. But the idea is that this is the straight line that will minimize the distances from the points to the line. So if this is the line of best fit, this is the straight line that has those distances minimized. Okay. Or you could also approximate these 4 points with a quadratic function or with any other function. So with a quadratic function, if you have 3 points, you might be able to find a quadratic function that will go exactly through those 3 points. But if you have 4 points, that may not necessarily be true. So perhaps your quadratic function will maybe go through this point, but it might go something like that. It doesn't mean that it will go through the 4 points. So that would be the best quadratic function that you can find. We could also approximate the point with the best cubic function or the best logarithmic function and so forth. So that's the idea. That's what we're going to do in this chapter. And also there's the second type of approximation, which is called the continuous approximation, which is basically approximating a given function. So here, for example, we have this function that is given, and you may ask, why do we need a new function if we already have the function there? Well, in some cases you would like to approximate this function with a simpler function, maybe with a straight line, right? What is the best straight line that will approximate this function here? Or perhaps you would like to approximate this function with a quadratic function. So there are many reasons why you would want to do that. Maybe the formula for this function here, for the s of x, is very complicated. Maybe you're using that in some kind of model, and in that model you really need to have just an approximation, a quadratic approximation, and then you would like to use that quadratic approximation to do something else. Anyway, whatever the case is, the purpose here is to approximate a complicated function or any function with a given with a type of function that you would like to use. So for example here, if I would like to approximate this function with the straight line, perhaps the straight line that will best fit the function would be this one, that will minimize the error. Okay. So, and that's what we're going to do. So the first topic is the least squares approximation. For those of you who know linear algebra, we've done this before, and the formulas that we get at the end are exactly the same, but it's a different approach. So in linear algebra, we use distance of vectors. We consider those functions that are vectors, right? And then we project those vectors on a subspace, and it's a very sophisticated approach and very very clever idea actually. When you take linear algebra, if you haven't done that yet, I think you will enjoy it. Anyway, the approach that we're going to use here is different, but it's a little bit longer, and I would like to say that it's more of a brutal force. The linear algebra approach is more sophisticated and cool. I really enjoy that. But this idea here is more a calculus-based idea. Anyway, so let's take a look at the first approach, the discrete approximation.